Hello, students. Today we want to talk about rational functions. Rational functions are ratios of polynomials. We've been talking about polynomials, some of the attributes and the ways that we can sketch polynomials using zeros in behavior and intercepts, things of that nature. What we want to do now is transfer that knowledge to the rational function, which is a ratio of two polynomials. And what we're going to find is that there's a lot of limiting processes going on that we will make an effort to intuitively understand. And when you get to the calculus, you will understand and study more of the arithmetic that is behind what's going on with some of these functions. So let me go ahead and share my screen. I think you will enjoy the work on rational functions. We really do get to use all of the work we've done on polynomials, and then the sign tests that we've cultivated will be very, very useful to us. So as you make your way through STEM, pre-calculus mathematics to calculus, we're going to see over and over that the mathematics we study is based on arithmetic, signs of numbers, inequalities. That comes up over and over, and we're going to see that to be the case with the rational functions. So as I said before, a rational function is a ratio of polynomials. And what I've done here, you can use any letters you like, but I'm using N for numerator and D for denominator. And so just giving you a basic generalized form of the polynomial. For the numerator, we have coefficients A sub I, and for the denominator, we have coefficients B sub M or B sub I, etc. So the degree of the denominator would be M, and the degree of the numerator would be N. So lots of times we find it very useful to refer to the generalized representation of the polynomial when we talk about asymptotes, especially horizontal. Now, as I've written here, we have R of X, which will stand for rational, is a ratio of two polynomials, as I've written here. And here's a very simple example of a rational function. That is, the numerator is 3x plus 4, the denominator is x squared minus 5. So that is a rational function by definition. Now, the very first object that we talk about with rational functions, again, that doesn't necessarily exist, but when it does, we have a way to define it. For instance, if the denominator has a 0c that is not a zero of the numerator, then x equals c is a vertical asymptote of the graph of R of X. That is, when you are asked to determine vertical asymptotes of a rational function or any quotient of functions, they don't necessarily have to be rational, you're looking for zeros in the denominator that are not zeros in the numerator. That is, they are isolated to the denominator. And if you have that situation occurring, and since the continuity that we get from calculus is shared by the rational functions, we actually get a situation where the function becomes unbounded. And what we do is we sketch a dotted line of the vertical asymptote to help us guide the drawing of the graph in the neighborhood of this particular C. So we will spend plenty of time sketching the vertical asymptotes. Just note here, we can use some calculus notation, which is very simple. That is the limit, for instance, as x approaches C from the right, we'll use a little plus there, of R of X. We could say, for instance, in any case, we could say this is plus or minus infinity, or just say it's infinity. This is an example of what we're talking about. And it could be the case if we approach from the left that we get a different sign of infinity, maybe negative infinity. So these are just examples of what you can expect. And then you might be thinking, how will you know what sign to affix to the infinity symbol? Well, we'll use our sign test. and above and below, just like we've been doing. And the sign test will give us the actual plus or minus that we affix to the infinity symbol. So we're already good at doing that. So we will continue to do that and have exactly what we need to draw our graphs accurately. So again, think of vertical asymptotes as the function becoming unbounded. And we can't draw a graph that goes on forever. I mean, that wouldn't be possible. So we use these dotted lines and have the graph hug the vertical line to show that the value is getting infinitely larger or just infinitely smaller, diverging to negative infinity. We'll do some examples. And the other object that, again, is new for the rational function is the so-called horizontal asymptote. And this is where we have to use degrees of polynomials to ascertain what type of horizontal asymptote we get. So if the degree of the numerator is less than the degree of the denominator, then the x-axis, or y equals 0, is a horizontal asymptote of the graph of r of x. So again, since we don't want to have to always write horizontal asymptote out, we'll just write h period, a period, just to save a little time. Just for vertical asymptote, we can just write v period, a period. So a lot of times we'll do something like this for vertical asymptote. Now, why it's very convenient to write these generalized forms, when the degree of n and the degree of d are the same, then we have a very simple relationship going on. Just this has to do with factorization. The horizontal asymptote will simply be the ratio of the leading coefficients here. That is, we'll take the ratio of a sub n to b sub m. That ratio will give us the horizontal asymptote. So again, when we pay attention to the degrees, we can get some very quick information about what is happening. And with the horizontal asymptote, this is what we call the limit at infinity. So for instance, we would say that the limit of r of x as x approaches infinity is some number L. And it could also be the case that as x approaches negative infinity, that we get the same number or a different number. So we could say equals k. Usually in our cases, we will have the same number being repeated, but it's certainly not required. So when we think of the vertical asymptote, we think of the function becoming unbounded. The infinity is in the nature of the function. When we look at the horizontal asymptote, we are thinking about what happens as x becomes arbitrarily large or arbitrarily small. Does the function value, or do the values of the function approach a particular number? Okay, and that's why we state that we have a horizontal asymptote, because the values of the function tend to cluster around a particular real number. Now, one thing that's interesting, and one thing that your book notes, is that if the degree of the numerator is one more than that of the denominator, then you get infinity as x proceeds to positive infinity or negative infinity, accepting a sign that you will have from the coefficients and the residue values of the x that you have after you divide. But the key here is that when this case occurs, and then of course if this number becomes a 2 or a 3 or bigger, then you don't get horizontal asymptotes. But in the case when the numerator is one more, you get what we call a linear asymptote, sometimes called oblique, sometimes called slant. There are many names for it. This is just basically a linear function, first degree in x, that you get as an asymptote. And again, instead of being a horizontal line, it is oblique or slanted. And you can actually determine this by just basic polynomial division. So again, there are two cases where we get a horizontal asymptote, and when the degree of the numerator is larger than that of the denominator, we can get a slant or oblique asymptote, and then after that, we could get a quadratic, a cubic, a fourth degree. It goes on forever. So you can get some really interesting graphs. The main thing at this point is that the values of the function are no longer approaching a real number. In this case, they're just becoming infinite. So there's a big difference in the quality of the graph. Now, for this to make sense, let's apply this to an example, and you can see how all of these new objects work for us. Again, we're going to approach this just like we're working with polynomials, but now add in the asymptotes. So let's take an example here. Let's take one where we've got the degrees equal. So we're going to say r of x equals 3x squared divided by x squared minus 9. Now, again, you can always make up functions and practice your craft of mathematics. Once, if you run out of problems to do, probably that won't be the case, but you can always make up problems and test your understanding. Now, the first thing we want to do is just look at this particular function. Notice, I always like to go back to things we've already done. If we look at the domain, and many times when you compute the domain, you uncover vertical asymptotes. So we get 3x squared. We'll just go ahead and factor this, x minus 3, x plus 3. The factored form is not always what we want to use, but it certainly could be something that helps us with our sign test dealing with multiplicities. So notice here in the domain, we would have to exclude 3 and negative 3. So this would imply that the domain of R is all real numbers except for, as I said, negative 3 and positive 3. Now what we want to do is now observe that in the numerator, 3 and negative 3 are not zeros of 3x squared. So this implies we have vertical asymptotes. Vertical asymptotes, x equals 3, x equals negative 3. These are vertical lines. That's what we call them, vertical asymptotes. Again, 3 and negative 3 are zeros of the denominator, but not zeros of the numerator. So they define vertical asymptotes. This is very important. Otherwise, you get a hole in the function, which is completely different. The function doesn't become unbounded. Now what we want to do, again, you might have already observed this, R is an even function. We have a symmetric domain, but R of negative x equals 3 times the additive inverse of x squared divided by negative x squared minus a 9. And that gives us, again, when you square the negative, it absorbs, so you get 3x squared. And of course, downstairs, the same thing happens, x squared minus 9. And that is indeed the original function. So this says, by definition, R is even. So that helps us when we draw the graph. We know we have to have y-axis symmetry. So that's another plus when we're working with rational functions. It certainly will assist us in drawing a more accurate graph. Now, let's go ahead and check out some other things that are very straightforward. We can look at the horizontal asymptotes. Notice here, we can, if you want to call this, again, the numerator n of x, and call this the denominator d of x, what we see is that the degree of n equals 2, which is also the degree of d. So now we can just use the ratio of the leading coefficients. So we have y equals 3 over 1, or 3 is a horizontal asymptote. So again, that gives us additional information. We dot in the horizontal line, and then as x approaches infinity and negative infinity in this case, so we can just note here, the limits that I wrote on the previous page, but what we'll do when we do our sign convention, we'll see what's actually going on, and then we can catalog all of the findings we get from the sign test. So we have horizontal asymptotes, we have vertical asymptotes. Let's just note that we have very simple, in this case, x-intercepts. So r of 0 equals 0. And then, of course, so that's really very easy. That's our y-intercept. And it's also an x-intercept because we know r of x is just 3 times, and I'll do this kind of like, so we see that that has a multiplicity of 2, and x minus 3, x plus 3. So this gives us boundary values, if you will, of 0, which has multiplicity 2. We have 3, which has multiplicity 1. And we have -3 that has multiplicity 1. So remember the way that we affect the sign test, and you'll do the same in the calculus, is we look for real numbers for which we have undefined, and we look for real numbers for which we have zeros, because that will indicate possible places in the domain of the function where the sign will change. And of course, we don't include the 3 and the -3, but we're thinking on either side of the vertical asymptote, we could get a sign change. So now let's go ahead and draw our number line so we can see what the convention will be. So we have -3, we have 0, and we have 3. Now, just like we did with the polynomials, we do exactly the same. And when we were doing the inequalities that we did at the beginning of the course, I was already doing the same thing. So we are refocusing on the sign convention to help ourselves really get the idea of inequalities and an efficient way to actually solve them. So now what we can do is go up here and then just replace x with just a very large number, just say like 100. So of course we look at the leading coefficients and we see that the value is positive clearly. And notice we have to, let me just write here, touch for the multiplicity, cross, cross. So we have plus and we cross, but then we touch, touch. So we still say negative, and then we cross. So this is not a graph. This is simply indicating above and below. So here we have plus, above. Here we have negative, below. Here we have negative, below. And let me write that a little bit better. Below. And here we have positive above. So we don't do anything any differently with the sign test. That's exactly the same as we've done before. Just think of this like doing an inequality, but we're not necessarily looking for positive or negative. We're looking for the totality of the signs so we can get a really nice picture. Now notice, okay, vertical asymptotes, horizontal asymptotes, we have intercepts. We pretty much exhausted pretty much everything we do. We even know that we have symmetry here. We've got an even function. So we have y-axis symmetry. Lots of times when you start to sketch a graph, you can get a reasonable graph with what you have. Okay, that you don't, it doesn't have to be Rembrandt, but it just has to basically present the characteristics of the function that you are equipped to give. So now let's go ahead and draw this. So we can write any kind of scale we like that will accommodate the space we have on our page. So don't worry about not having enough space, just space things in a way that makes sense. So of course now we have y equal 3. So we have 1, 2, 3. So we can dot in the line y equal 3. Do the same here. And we can use the sign convention to affix the particular values of plus and minus infinity. And then we have 1, 2, 3. So 1, 2, 3. We'll just space them out a little bit more on the y-axis, x-axis if you like. So we have x equals 3. And then we have 1, 2, 3 to negative 3. So we have x equals negative 3. Now, notice, and what's interesting about this particular graph is that now we can use the sign convention to figure out what sign we affix to infinity. So let's do the simple part first. Let's go between negative 3 and 3. So notice, since we're below here, we must diverge to negative infinity as we approach negative 3 again from the left, or from the right. And then as we approach 3 from the left, we're still approaching negative infinity because the sign is negative. Again, we don't ever get to 3, so we just look at the sign that we have in the path leading up to 3, here from the left, here from the right. And then we have our x-intercept right here. So we're going to pick that up and make it look even. So this will give us a nice picture. Doesn't have all the detail maybe we'd like, but it'll have sufficient detail. So this will give us a rendering that has y-axis symmetry. We hit the x-intercept. Can't hit any other place because that's the only 0. And again, the sign does not change. Just like we have here, the sign does not change. It's multiplicity 2, even. And then we use the sign convention to say, now what happens as the to the limit of r of x as x approaches negative 3. In this case, from the right, we get negative infinity, and we get negative infinity here. So let me write that down. So we have the limit using the calculus notation, x approaches negative 3 from the right of r of x will be negative infinity, and the limit as x approaches 3, again from the left of r of x, will be negative infinity. Now, you don't have to write these down for all of them. I mean, but this is what's going on. And now we can easily complete the graph by noting that as x approaches infinity at negative infinity, the graph must hug the horizontal line y equal 3. But notice, and I'll extend these vertical asymptotes a little bit into our other stuff. Notice here we're above, and so the positive infinity is assigned as we approach 3 from, in this case, the left. And then as we approach negative 3 from the right, we have positive infinity. So we get something like this. And then approach y equal 3, and then do the same on the other side using symmetry. Like this. So we end up with a graph that is very reasonable. Again, the calculus will provide a better configuration for the shape. Notice how we've basically, when we draw this, we infer a type of shape, which we think must be that way because we've seen many pictures of polynomials before. And as we draw it, it looks like we have an upward concavity here and here. And here we have a downward concavity in the sense that if we were thinking about drawing tangent lines, the curve is falling away from the tangent line here, and then it's moving above in the other case. Let me fix this, sorry. So what we're seeing at this point is that from the sign convention here, which is extremely useful, the asymptotes, multiplicities, and use of intercepts, we have a very, very reasonable graph. And then, of course, in addition, noticing the y-axis symmetry that we get because the function is, in this case, even. Now, of course, not all functions are even, nor are they odd, and so we don't always have that luxury. But just notice the most important ingredient in all of this, the BVs, which are intimately tied to the vertical asymptotes in the domain, and again, the zeros. Then the sign convention, using the multiplicities and establishing an extreme value in the sign. So take an extreme value that is greater than a BV and establish the sign, and then move through the zeros and the BVs using multiplicities. Now what's interesting here, we know we don't really cross at the -3 and the 3 because that's not in the domain. So if you want to break your line, you can. Notice this, the x equal -3 is not part of the graph. It just helps us draw it. But what I've done here is just indicate that when we are to the right of -3, we are negative. When we're to the left of -3, we're positive. So if you want to break the line, you certainly can. But this establishes the sign convention, and the sign convention tells us how to affix the plus or minus infinity. That is, what do we attach to infinity, a plus sign or a minus sign? And that's all indicated by our little sign chart. And it gives us all the information we need. So let's try another one. Remember, when we talk about rational functions, we're looking at ratios of polynomials. So let's see here. Let's get another one that has some interesting features. Well, that one's, let's see here. Oh, this one, this will be interesting. It doesn't have as much stuff in it, but it'll be a good example. So let's say we have x, and then we have x squared minus 4x minus 5. So let's get some practice with the different types of horizontal asymptotes. Now notice here, just like with the last one, the first thing we want to try to do is look for zeros in the denominator. So we can go ahead and factor. And notice with the AC, we have -5, which is just what, -5 times 1. That'll give us what we need. So we have x minus 5 times x plus 1. So that gives us a rendering that now says we have two zeros in the denominator that are not zeros in the numerator, namely -1 and 5. So this implies we have a domain of R, which in this case is -infinity to -1, union -1 to 5, union 5 to infinity. Now, of course, we have vertical asymptotes. X equals 5, x equals -1, because these are not zeros in the numerator. So if you want, you can think of the polynomial upstairs as n of x, the polynomial downstairs as d of x, just as a reference when you want to look at degrees. So again, when you compute the domain, that's usually the biggest indication of the existence of the vertical asymptotes. Just remember, if the zero in the denominator is repeated in the numerator, then you do not have a vertical asymptote. So that'll just be a hole in the function, because those particular factors will absorb. And then the function will just not have a definition at the zero. So there'll be a hole. That's it. The function doesn't become unbounded. So be aware of that, and don't fall into that trap that you just get zeros in the denominator and claim that they're vertical asymptotes. Be careful with that. Now the other thing that we want to notice is degrees. The degree of n is 1, and the degree of d is 2. So this implies, again, the degree upstairs is less than the degree downstairs. So we have y equals 0 is the horizontal asymptote. horizontal asymptote of the graph. So remember, in the previous example, we had a situation where the degrees were the same. So we got ratio of leading coefficients. But notice here, the degree in the numerator is less. And so we get the horizontal asymptote y equals 0. And that just has to do with the fact that as x becomes arbitrarily large, the denominator grows much more quickly because of the larger power. And so the values of the function converge to 0. And that's exactly why we have this. And that can just be shown through factorization. And is not overly difficult. We just have to establish some limits that we now just do intuitively, which we will make more arithmetic when we take the calculus. Now, with that said, let's also make a note of all the BVs, the boundary values. We already have the zeros for which the function is undefined. We've got 5 and -1. So we have 5, which has a multiplicity of 1. We have -1, which has a multiplicity of 1. And then we have the 0 in the numerator, which is just 0 of multiplicity 1. So all of these are odd multiplicity. So we have cross, cross, cross. That's very important. That establishes the sign convention, which is also going to help us as we attach the correct plus or minus sign to infinity. So this, I guess when we think about it, this sign convention that we do is probably the most important to getting a correct graph. So let's go ahead and plot these. We have a -1. Just space them out so you can see them, 0 and then a 5. Now, always adhere to the convention that you have that's most easiest to check. So now, of course, think of a number like 500. Okay, so we put the 500 in for x, and of course, the 500 upstairs is fixed because we just have the x. And then, of course, the square downstairs will dominate these two terms. So we clearly have a positive output. So if we're plus here, we just cross at all of these zeros in undefines. So we have plus, so we cross, cross, cross. That's it. Now, again, we're not really crossing at the vertical asymptotes. I mean, you can put a little gap there if you want, but we are establishing the sign on either side of the asymptote, so we know whether or not it's positive infinity or negative infinity. This, like I said before, you will continue to do with the calculus, and it'll be the easiest way to determine sign of first and second derivatives quickly. And of course, when you're working with trig functions and exponential functions, logarithmic functions, it's really going to be handy to have that understanding. So we have above, we have below, we have above, so plus, and then we have below. So the idea here is that, again, we know how to affix the plus or minus to the infinity, and we know how the interaction is at the zeros, and there's only one. We just have to cross. Now, one thing we can do, we just notice this, the x-intercept is the 0, so we just have 1. Sometimes we have more than 1 if the numerator is more crowded, so x-intercept is just 0. And then, of course, r of 0 is also 0. So those coincide again. Now, this, because the zeros aren't symmetrically distributed, we don't have an even function, clearly, nor odd. I mean, it's neither, but that's okay. We'll survive. So let's go ahead and draw our picture. And now we'll draw in our asymptotes at 1, a -1, and 5. So let's see, 1, 2, 3, 4, 5. So we have x equals 5, and then we have -1. Spread it out as much as you can. You don't have to make everything tight. Just spread it out so you can see it. You are in command when it comes to that. And so now, of course, we have the 0 at 0. And notice now we can look at the sign convention. So if we just go ahead and look at this part, notice we're above here to the right of -1. So we have to come this way and pick up the 0. And then notice as we move down, we have to now proceed to -infinity because we're below here. So the sign attached to infinity here is negative. And of course, here it's positive. So we just hug, 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 pick up the 0, and then down here. I like that. Now, of course, this is not Rembrandt, but we make it look as nice as we can, keep it nice and smooth. There we go. So we hug, and then we pick up the 0, and then we ascend to -infinity, just like that. That's it. Remarkable how easy this is. And of course, we have y equals 0 is the horizontal asymptote. Now, notice we've covered this part. Now for the 5, greater than 5, where we have to hug the vertical asymptote, but with positive infinity, and then we hug y equals 0 because there are no more driveways here. So we do something like this. There you go, like that. So hug, positive infinity, as we see the plus, and then y equals 0. And then we do the same over here. Notice we have to do the sign convention. So when we look at the -1, notice we're below the x-axis. So we have to hug at -infinity and then approach the 0, y equals 0 here. So the sign convention basically says we must be below the x-axis. So we attach the negative sign to infinity here and then hug the y equals 0 from below. Just like that. And look how quickly we can get a graph just using the sign convention. As I said before, the sign convention is critical. If you get your BVs, again, looking at the vertical asymptotes, your zeros, check the multiplicities, then you're covered. And now you have a graph that more than indicates a reasonable picture. Now, here's something that you might be thinking about. Will the calculus tell you why the graph looks this way here, especially if we got to hug this line and then hug this vertical line? We think the graph would have to look something like that, and that's due to continuity and differentiability. Again, no breaks in it and smooth, but of course we have an infinite discontinuity here and here. Calculus will tell us about that. And so it looks like we're decreasing, decreasing, decreasing. The graph is falling. The graph is falling throughout the domain. So we're thinking, we drew it, and using the sign convention, we believe that this is what the graph would look like. And the calculus will also verify the fact that this function is always decreasing. But I want to share with you a very important point here. These techniques are critical. And so when you get to the calculus, you will continue to use these. You will simply use the calculus to verify what you're doing, and then also investigate some other types of functions that may not allow for as efficient of an assessment with these techniques, where the derivatives will have a larger role. But we must understand, and this is very important, the techniques that you learn in the pre-calculus mathematics will be taken to calculus, and they will assist you in creating the correct picture. That is, finish the job, so to speak. Let's get everything else so we know that this picture is exactly what we think it should be. So that's what's neat about the rational functions. And then another thing we can think about, ladies and gentlemen, is we know what the domain is, and then we can think about the existence of the horizontal asymptote. So it appears that we can get as close as we like to zero from below and as close as we like to zero from above. But what we're finding also here, we pick up the zero. So all real numbers for the range. Now that's not a quick proof. I mean, it's not, we can't reason from the picture, so to speak, but we would be very confident in saying what our analysis has indicated is that our output could be any real number. Notice as we look here, we don't get the zero, but notice we have the zero. So we could confer, or at least infer from our work here, that we have a range of all real numbers. That is, range of R is all real numbers. And that can just be done by picking an R and doing cross multiplication and solving the quadratic, which is a very, very useful technique in determining ranges of rational functions. So we get an immense amount of information using the very straightforward techniques, and we see that the sign analysis is critical. So remember, with the rational functions, we just have the two new objects. Everything else is the same. We have the vertical asymptotes, we have the horizontal, and now we're going to do a case where we get the oblique asymptote, where the degree of the numerator is one more than the degree of the denominator. Now, as you continue in the calculus in other classes, you may see degrees being 2 and 3 larger, where you get quadratic and cubic asymptotes, and that'll be interesting. But we won't be focusing on that for now, but just be aware of that. So let's try another one. Here we go. So we've got, let's look at this and say we do 2x plus a 3, and I'll say R of x. Well, let me do this. Let me put a little bit more space there so I don't run out of room. So we've got example, R of x equals 2x plus 3 divided by x squared minus 4. Okay. And let's see here. Well, this is what we did for the last one. Let me make one little change here. I want to make sure that we get the degree one bigger. So let's do this. Let's do this x here, and we'll square this here. There we go. That's what we need. That'll look a little bit better. Now let's make some inferences here. Notice we'll call this the numerator, and we'll call this the denominator. And we have the degree of the numerator is 2. The degree of the denominator is 1. So this implies degree of n equals 1 plus degree of d. And that implies the oblique asymptote. No, I looked at some examples and I'm thinking I'll just make up my own. And so we'll go with this one. So this gives us the oblique asymptote. Now, in order to figure out what the actual oblique asymptote is, we just need to do some polynomial long division. So let's do that first. So we have x minus 4, and we have 2x squared, and we'll do a 0x because we don't have an x term plus a 3. I tried to set this up so we can focus on the oblique asymptote. So now x into, of course, we could use synthetic, but I haven't taught you that yet. So we'll just do this the long way. So this will give us a 2x. So 2x squared. And then, of course, we have a 2x times a negative 4, which is a negative 8x. So now we subtract. So that gives us a positive 8x plus a 3. Now we can divide again. The degrees are the same, so we can keep dividing. So this gives us a plus 8. And so we have 8 times x, which is 8x. And then we have 8 times negative 4, which is a negative 32. And we subtract, and we get a 35. So we just have 32 plus 3. So this implies r of x equals 2x plus 8 plus 35 divided by x minus 4. So this gives us a little bit different presentation of r if we just use basic polynomial long division. Of course, when I say more about synthetic, I'll show you how to do that, but I haven't taught you that yet, so we'll stick with this. Now, notice as x gets arbitrarily large, this term will get very, very close to 0. That is, as x gets infinitely large, this will converge to 0. And as x gets very negatively large, this will also converge to 0. So the only thing that really survives is this. So when the values of x are infinite, plus or minus infinity, the function will start to behave like this linear function, 2x plus 8. So this is what we say. Let's write this. So the y equals 2x plus 8 is the oblique asymptote. Oblique asymptote. So I wanted to do an example where we cover all three types. That is y equals 0, y is the ratio of the leading coefficients, and then where we have the degree of the numerator, one more than the degree of the denominator, which gives us this. So we're good with this. Now notice, let's go ahead and do all of the other analysis. We're done with the oblique. There's clearly no horizontal. We've got the oblique. We're covered with that, with the division. Now we've got a 0 in the denominator, which is clearly not a 0 upstairs, but you see there are no zeros in the numerator. So we have a vertical asymptote of x equals 4. And observe, very good word, observe 2x squared plus 3 is always positive. No real zeros. Now, we did an example where I went ahead and factored the polynomial to show the imaginary zeros. This clearly has imaginary zeros. And again, we'd have the, the square root of 3/2, I plus or minus I. And I mean, that's fine, but we're not going to see any of this in the real Cartesian real graph. So don't worry about that here. So we clearly have vertical asymptote here. We have no x-intercepts. And then, of course, if you notice, r of 0, just replace x with 0 and we get negative 3/4. So that's the y-intercept. So y-intercept, negative 3/4. So we get that very easily. Now, if you make some other observations here, of course, the square would absorb a negative, but when we look at the domain, let's just go ahead and write the domain. The domain of R will be all reals except 4. So we have negative infinity to 4. Union 4 to infinity, and that's clearly not symmetric. So we're kind of dead in the water with even and odd, but that's okay. Now, you're thinking, what's the last thing we have to do? The sign convention, and that's it. Now let's write down the BVs. You're thinking, this is not a whole lot here, Professor Hollis. There's just not much here at all. Notice, this is never 0, okay? But it is undefined at 4, so there's only one BV. That's it. So how simple. So we've got 4 here. And then, of course, if you put in, 500, that's clearly positive, and that's got multiplicity 1. So I'll just say multiplicity 1. So we just do something like this. So we have plus above and then negative below. So that's it. That's it. I mean, that's how simple this is. So as we look at the vertical asymptote, as we approach from the right here, we're at positive infinity. As we approach from the left, we're at negative infinity. And then as the graph, as x gets large positively and negatively, it will approach the linear function here. So let's just dot in the linear function and the asymptotes, and we should be good. So we can do this really simply so it doesn't, take forever. So notice we'll do the scale so it's a little bit easier to do. We have in this case, a y-intercept of 8. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. You don't even have to be that specific, but we've got that. And then, of course, if we put in a -1, we get a 6. So I'll spread this out a little bit more. So 1, 2, 3, 4. We'll spread this out a little bit more. Won't look so good, but we'll spread this out more. And then, of course, we get -1. We get a little 6 there. So let's go ahead and dot this in. Of course, we go into the work, but that's okay. That's what happens when you do these types of calculations. Then, of course, when we set this to 0, just do that. Just say this is 2 times x plus 4. So we get a -4. So I'll try to draw it so it looks pretty good. There we go. So that's not half bad. So we have, in this case, y equals 2x plus 8. And then we have our vertical asymptote at 4. So I'm extending this all the way up here. So yeah, there we go. That's what happens. I don't want to do this on a separate page because then you can't see all the work I've done. So this just goes on up here, and we'll just extend this on into our work, okay? So now notice we don't have any x-intercepts. We do have a y-intercept of, where did I put that, -3/4? So that's about right here. So yeah, I'll cheat a little, put it about right there. So we have to hug this, and then we have to move over here and hug that. So the sign convention requires that we have something like this. And then hug this line all negatively. So we affix the negative sign to infinity here. And so we have to pick up the y-intercept and then hug the asymptote. Now up here, we're not down here because we can't be. We don't have any driveways. There are no x-intercepts. So we have to hug here and then hug here. So I had to draw my graph up into the work here. So we get something like this, like that. So our graph goes into the work, but here's the interesting thing. The calculus will supply a relative maximum here, which we're not really sure where it is with this type of analysis. And then we're thinking we'll have a relative minimum here, and that will be revealed through the calculus. So just remember, this slant asymptote is this slanted line. It's not horizontal. And what is the key? Just like I said before, draw the asymptotes as guides and then use this sign convention to tell you where the graph has to be. Notice we have to hug this line, but we also have to ascend to positive infinity. And so we've got to do something like this. And you can easily test this. We do not cross this slant asymptote. You can actually set this function equal to our slant asymptote and show that you get no solution. And the idea here is that when we do the calculus, we will verify the concavity here and here, and we will also be able to determine the relative maximum and the relative minimum. But this is an excellent graph. Let's just write what we have. So we have the graph of R of X equals 2x squared plus 3 divided by x minus 4. So again, in summary, we started with the degree of the numerator, one more than the degree of the denominator. We use our basic polynomial division to determine the oblique or slant asymptote. And we see that the function will approach these values again as x gets positively infinite and negatively infinite. We see we're approaching the slant asymptote here and here. And then, of course, with the sign convention, we have our vertical asymptote x equal 4. We approach negative infinity when we're to the left of 4. And when we're approaching to the right of 4, we approach positive infinity. Again, the unboundedness is also a function of the sign of the function, the pluses and minuses. So that's how we affix the plus or minus to infinity using the sign convention. So now what we're seeing as you work with the rational functions, analyze the vertical asymptotes, horizontal asymptotes if they exist, or the slant asymptote. When you compute domains, you pretty much run right into the vertical asymptotes. Make sure you have zeros in the denominator that are not zeros in the numerator. And you do your BVs, so that includes the undefined and the zeros. So that will necessarily mean that you have to try to solve the numerator. But we see here, this has no real zeros. So we only have one BV. So this is a really interesting problem that does take some analysis, but it's actually quite simple because you can't violate the sign convention. The sign convention dictates above or below. So notice here, the graph is below the x-axis, and here it's above, and the vertical and the slant asymptote basically demand that the graph have this shape. So just remember all of the information that we've learned about polynomials, we transfer to the rational functions. And then we add, what do we add? We add the vertical and the horizontal and the slant. That's it. All the sign convention, everything else, the inequalities. Just remember, when we do the sign convention, we're not looking at a specific inequality. We're looking at drawing the graph. So we need to know the pluses and the minuses all throughout. Now, of course, if you think about this sign convention here, you can see that this particular function will be less than 0 on this infinite interval from negative infinity to 4, and you'll see it's positive from 4 to infinity. So at least, I mean, what we're seeing here is that this BV technique is just indispensable. It gives us a large amount of information that is required to get an accurate graph. And then as we continue on, we will learn more about the precision of the graph and what we can glean from the calculus to add the last pieces of the picture. Well, I think you're going to enjoy the rational functions. Again, the beauty of the pre-calculus mathematics is to work with the arithmetic, work with the algebra, get very competent. So when you start working with the calculus, the differentiation, the limits and things like that, you have a competence that actually allows you to enjoy learning the calculus. So put plenty of time into the polynomials and the rational functions, and I think it will definitely pay off. So that's all I have to say about this, and we'll see you soon. Thank you.